Welcome back to the deep dive. I have to be honest with you, and I think a lot of our listeners probably feel this way too. It feels like we're standing in front of a fire hose right now.
That is probably the most uh, the most apt description of the current state of artificial intelligence I've heard in a long time. It is relentless.
It really is. I open up my news feed or I'm looking at a tech blog, and it's just this absolute alphabet soup. You've got RNNs, CNNs, VITs, Transformers.
SSMs now.
It feels like every single week there's a new acronym that supposedly changes everything. It's getting to the point where, I feel like I need a PhD just to read the headlines.
Oh, it's incredibly easy to feel overwhelmed. And when you look at the field from the outside, it just looks like this chaotic zoo. You have one specific tool for pictures, and then a totally different tool for text, another for audio.
And they all have these completely separate, complex names.
Yeah, exactly. It feels like you're just memorizing a catalog of random parts.
Right. It all feels so disconnected. But that's why we're here today. We're going to try to turn that fire hose down to a manageable stream. We're digging into a lecture by Paul Liang from MIT.
From his course, How to AI Almost Anything.
And the reason we picked this source is because Liang makes a pretty bold claim.
He really does. He argues that we need to stop looking at all these acronyms as, separate, disconnected islands. He thinks there's a unified framework.
A sort of shared DNA.
Yes, a shared DNA that connects a simple image recognizer from, say, the 1990s to a massive large language model like GPT-4.
Which sounds fantastic because I would love a mental model that actually connects all these dots. But before we can get to that unification, the theory of everything, so to speak, we have to talk about the context he sets up, because he starts with two concepts that seem to completely undermine the idea of studying architecture at all.
He really throws a wrench in the gears right out of the gate, doesn't he?
He does. He talks about the bitter lesson and this weird phenomenon called grokking. So let's unpack the bitter lesson first. This comes from a researcher named Rich Sutton.
Yes, Rich Sutton. And to be honest, for a computer scientist or, a software architect who has spent their life designing these clever, intricate systems, the bitter lesson is a very hard pill to swallow.
Why is it so bitter? What is the lesson?
The lesson is, essentially, stop trying to be so clever.
Okay.
Sutton's argument is that if you look at the history of AI over the long term, the general-purpose methods that just leverage massive computation.
So raw processing power.
Exactly. Just throwing raw processing power at the problem.
Yeah.
They almost always beat the clever, complex architectures that are designed by human experts.
Wait, so all that work of trying to design the perfect digital eye or mimicking how the human brain processes grammar, you're saying all that specific design work just loses out to a big, dumb machine?
In many cases, yes. Sutton argues that our human inductive biases, that's the fancy term for the expert knowledge and the rules we try to bake into the model, they eventually hold the model back.
So when you have enough scale, the computer just figures out better rules than we can teach it.
That's the idea.
That is
Yeah.
humbling. It's basically saying, don't think, just compute.
Pretty much.
So that leads me to a pretty obvious question. If the bitter lesson is true, why are we even doing this deep dive? Why spend the next 15 minutes on architecture? Why don't we just tell everyone to go buy more GPUs and call it a day?
And that is the million-dollar question. The answer is practicality. Not everyone has $1 trillion for compute. Not everyone has the entire internet's worth of data to train on.
Right.
If you're a researcher trying to discover a new drug or a startup trying to put AI on a small drone, you don't have the luxury of infinite scale. You need efficiency.
Okay, so architecture is how we survive when we don't have $1 billion budget.
Precisely. Architecture lets us be efficient with data and with power. And that actually links to the second concept Liang brings up, grokking.
This one I found fascinating. It sounded almost like a ghost story.
It is a bit spooky. Grokking describes a situation where a model looks like it's completely failing. You're training it, you're feeding it data, and the error rate, it just isn't moving. Or even worse, it's overfitting.
And remind us what overfitting is.
Overfitting is when the student, the AI, is just memorizing the answers to the test.
Without understanding the material.
Exactly. It can recite the training data perfectly, but if you give it a new question, it has no idea what to do.
Okay. So usually if you see a model doing that, you'd pull the plug, right? You'd say, this isn't working.
In the old days, absolutely. You'd kill the training run, save the electricity. But this grokking phenomenon shows that if you just keep pushing, sometimes for thousands of steps past the point where it seems to make any sense, suddenly the performance spikes.
It just clicks.
It just clicks. It moves from memorizing to actually generalizing.
It's like studying for a calculus exam, getting every practice problem wrong for 10 hours straight, feeling totally hopeless, and then at hour 11, your brain just snaps into place and you understand the underlying logic.
That's a great analogy. It suggests there's some complex internal transition happening that we don't fully see. But, we can't always rely on that magic. We need a map. And that brings us to the core of Liang's lecture, the modeling paradigm spectrum.
Okay, let's visualize this. He lays out a spectrum of how we build these things. On one end, you have the craftsman approach.
Right. The domain-specific models. This is where you bake in specific rules about how the world works. You're guiding the AI with your human expertise. Think of this as building a sniper rifle.
Custom made for one target.
Exactly. Highly efficient, but it takes a lot of skill to build.
And on the other end?
General purpose.
Yeah.
This is the bitter lesson end of the spectrum. You take a massive off-the-shelf model like a generic transformer, and you just throw data at it. This is the nuke.
It solves the problem by overwhelming it.
Right.
So for the listener who's actually trying to build something, maybe they're an engineer or just an enthusiast, how do you choose? Do I build the sniper rifle or do I buy the nuke?
Liang suggests it comes down to what he calls the modality profile. You have to profile your data and your constraints. Is your data noisy? Is it structured? And crucially, what are your resources? If you're running this AI on a smartwatch, you can't use the nuke. You need the sniper rifle.
So understanding the architecture is what lets you build things that work in the real world, where we have battery limits and budget caps.
Efficiency is the key word for this entire discussion, and that leads us to the unified view. Liang argues that almost every deep learning model, no matter how fancy the acronym, essentially does just two things over and over again.
Just two steps.
Just two. Step one, learning representations.
Walk me through that.
You take raw, messy, high-dimensional data. So think about a photograph. It's millions of numbers for pixel colors. Pixel 400 is red. Pixel 401 is slightly darker red. That's raw data. Step one is transforming that into abstract, useful information.
So you're turning Pixel 400 is red into this is the edge of an apple.
You got it. You're extracting features. And then step two, combining representations. You aggregate all that information. You use math concatenation, addition, attention mechanisms to combine those little features into a bigger picture.
So extract features, then combine them. Extract, combine, repeat.
That's the rhythm of deep learning. But, and here's where it gets really interesting, how you do those two steps depends entirely on two golden rules. If you get nothing else from this deep dive, remember these two terms, invariance and equivariance.
I have to admit, when I saw these words in the lecture notes, my eyes kind of glazed over a bit. They sound like terms people use to sound smart at parties.
They do, but Liang seems to think they are the physics of AI.
So let's break them down. Start with invariance.
Invariance is actually a very simple concept. It just means that if I change the input in a certain way, the output should not change.
Okay, abstractly I get it, but give me a concrete example.
Okay, imagine you show an AI a picture of the number 3 handwritten on a sticky note. The AI's job is to tell you what number it is. If you shift that 3 slightly to the left or rotate it a tiny bit, what should the AI say?
It should still say, that's a 3.
Right. The 3-ness of the number doesn't change just because I move the paper.
So the label is invariant to the position.
Exactly. The result stays stable even when the input transforms.
Okay, I'm with you. So what is the other one? Equivariance.
Equivariance is the opposite. It means if I change the input, the output should change in a corresponding, predictable way.
When would we want that?
Think about a self-driving car. It's analyzing a video feed to find the lane lines on the highway. If the car drifts to the left, the image of the lane lines moves to the right in the camera frame.
Okay.
Well, if the AI is telling the car the lane is right here, that internal map needs to shift exactly as much as the image shifted. If the input moves, the output map has to move with it. If it didn't, the car would think the lane is where it used to be and you'd crash.
Got it. So invariance means ignore the change, and equivariance means track the change.
Perfect.
But here's the part I'm struggling with. Why do we need to program this? Isn't learning the whole point of AI? Why can't I just show the model a million pictures of a 3 in different spots and just let it figure it out?
You can. That's the nuke approach.
Yeah.
But think about the cost. If you don't build these rules into the architecture, if you don't tell the model, hey, moving the 3 doesn't make it not a 3, the model has to learn that from scratch.
So it sees a 3 in the top left and learns it. Then it sees a 3 in the bottom right and thinks, ooh, new concept.
It treats them as totally separate facts. You're wasting massive amounts of training time teaching it something you could have just told it up front. You need exponentially more data to learn something that could have been designed.
And this is where the lecture brought up the factorial explosion. This was the section on sets, right?
Yes, the case study of sets. This really helped the math click for me.
Let's walk through it.
Okay, imagine you have a task. I hand you a stack of 5 photos of different actors, and your job is to tell me if Brad Pitt is in the stack.
Simple enough?
Does the order I hand you the photos matter? If I give you photo A, then B, then C, versus giving you C, then A, then B.
No. Brad Pitt is either in the pile or he isn't. The order doesn't change the answer.
Exactly. That is permutation invariance.
Mm-hmm.
The order implies nothing. So if you're building an AI to solve this, you need to structure it so it ignores the order.
How do you tell a computer to ignore order?
You use a technique called parameter sharing. So imagine you have a little face scanner algorithm. You use the exact same scanner for every single photo in the stack.
So you don't have a specific scanner number 1 for the first card and scanner number 2 for the second.
Right. It's one tool applied 5 times. And then to combine the answers, you use a math function that also doesn't care about order, like sum or max.
Yeah.
1 plus 2 plus 3 is 6, and 3 plus 1 plus 2 is still 6. The math is blind to the sequence.
And if we didn't do that, if we treated the stack of photos like a specific sequence where order mattered?
Then you hit the factorial explosion. This is where the efficiency argument becomes undeniable.
Mm-hmm.
If you have just 5 photos, do you know how many different ways you can arrange them?
I recall from high school math, it's 5 factorial.
Right. 5 times, 4 times, 3 times, 2 times 1. That's 120 different combinations. If your model cares about order, it has to learn all 120 variations just to understand it's looking at the same group of people.
So you are doing 120 times the work for the exact same result.
And that's just for 5 items. Imagine a data set with 1,000 items. The number of combinations is more than the number of atoms in the universe. If you don't bake in invariance, the problem becomes, well, unsolvable.
That really puts the efficiency point into perspective. It's not just about saving a little time. It's about whether the problem is even possible to solve.
Exactly. So that covers sets where order doesn't matter. But what about when order does matter? Like language.
Right. The bear ate the man versus the man ate the bear. Same words, very different outcome for the man.
Correct. So now we're moving into sequences. Text, audio, code. Here, the rules change. We need invariance to time, but equivariance to order.
Invariance to time meaning. The meaning of the sentence doesn't change if I say it at 9:00 a.m. or 5:00 p.m.
Right. But the relative order is everything. And this is where we see the evolution of natural language processing. We started with RNN's recurrent neural networks.
The lecture used a snowball analogy for this, right?
Yes. Think of reading a sentence like rolling a snowball down a hill. You read the first word, it sticks to the snowball. You read the second word, you add that information, you process sequentially, step by step.
So by the end of the sentence, the snowball holds the meaning of the whole thing.
That's the idea. But the problem with the snowball approach was speed. It was incredibly slow because you can't process word number 10 until you finish rolling over word number 9.
It's a bottleneck.
A huge bottleneck. And that is what led to the transformer, the architecture that basically ate the world. It solved the speed problem.
Liang describes it as essentially just fancy matrix multiplication.
Which is a bit reductive, but it's accurate. Instead of rolling the snowball one step at a time, the transformer looks at the entire sentence at once. It swallows the whole paragraph in a single gulp. This allows for massive parallel processing.
But wait, I feel like we just walked into a trap. If it swallows the whole sentence at once, like a big soup of words, how does it know the order? We just said order is the most important thing in language.
Right.
If man and bear go into the soup together, how do we know who ate whom?
Yeah, that is the genius part. Since the transformer processes everything in parallel, it naturally loses the order. So the engineers had to manually put it back in. They used something called positional encodings.
What is that, effectively? Little tag.
Yeah, it's basically a tag. Imagine sticking a little label on every word. I am the first word. I am the second word. So even though the model processes them all simultaneously, the math still knows where each word sat in the original line.
Okay, so we tag them. And then how does it figure out the meaning? How does it know bank means riverbank and not money bank?
That is the attention mechanism. For every single word, the model calculates a relevance score against every other word in the sentence. It asks, How much does the word bank care about the word river?
And if the score is high, it links them.
Exactly. It's doing this massive parallel geometry to find relationships, not reading left to right. It's looking at a whole web of connections at once.
It is wild to think that what we call intelligence is really just calculating relevant scores between words.
It's just math finding the most efficient structure.
Okay, let's move to the final domain. We've done sets and sequences, now space, vision.
And this is where the difference between a naive and a smart architecture is most obvious. The lecture contrasted the old wavefully connected networks with CNNs.
Right.
So imagine you have a small image, just 200 by 200 pixels. That's 40,000 pixels. If you try to use a fully connected network, you are connecting every single one of those pixels to every single neuron in the next layer.
That sounds like a mess of wires.
It's millions of connections. It's huge and slow. But worse, it lacks that spatial invariance we talked about with the number 3.
Because if I shift the picture, the fully connected network gets confused.
It treats it as a totally new event. It has to relearn what a cat looks like in the left corner and then relearn it in the right corner.
So enter the the convolutional neural network, the keyhole approach.
Exactly. Instead of looking at the whole image, you look at a tiny patch, say 3 by 3 pixels, and you slide that little window across the entire image.
And here comes that phrase again, parameter sharing.
It is the secret sauce. You use the same filter, the same edge detector on the top left patch as you do on the bottom right. You assume a vertical edge looks the same no matter where it is.
Which saves a ton of memory.
And it forces the model to be spatially invariant.
Now, before we wrap up, we have to mention the vision transformer, or VIT, because I thought transformers were for language.
They were. But recently, researchers asked, what if we treat an image like a language?
How do you turn a picture into a sentence?
You chop it up, you cut the image into little squares patches, then you string those patches together in a line, just like words in a sentence. You tag them with positional encodings, and you feed them into a transformer.
That feels so counterintuitive. You're destroying the grid structure.
You are. But because you're using attention, because the model can look at all the patches and see how they relate to each other, it reconstructs the image understanding. And it turns out, if you have enough data, this works incredibly well.
This leads us to the final segment of the lecture, which I honestly felt was the mind-blown moment, the grand unification.
The everything is a graph epiphany.
I always thought graphs were for specific things, like analyzing a social network.
They are. But Liang argues that every architecture we just discussed, RNNs, CNNs, transformers, they're all just special cases of a graph neural network.
Walk me through this. How is a photo a graph?
Well, think about the definition. A graph is just nodes,
Yeah.
which are data points, and edges, which are connections.
Okay.
Start with a graph. Set those photos of actors. That is a graph where the nodes have no edges. They are disconnected islands.
Okay. And a sequence.
A sequence, like a sentence, is a graph where the nodes are in a straight line. Fox connects to jumps, jumps connects to over. It's a line graph.
And an image.
An image is a graph where the nodes are pixels arranged in a grid. Each pixel is connected to its neighbors. Up, down, left, and right.
So when we debate between a CNN or a transformer, we aren't picking different species. We're just defining the rules of the relationships. We're just deciding who is neighbors with whom.
Precisely. The DNA is the same. The architecture is just a way of hard-coding the connectivity to match your data. You don't use a grid graph for a sentence, and you don't use a line graph for a pile of photos.
That is surprisingly beautiful. It makes the whole field feel less like a zoo of random animals and more like a single system adapting to different environments.
That is a great way to put it.
So bringing this back to the listener who has survived the fire hose, we've covered invariance, equivariance, graph theory. What is the big takeaway? If I'm looking at a data set tomorrow, what do I do with this information?
The takeaway is that designing a model isn't magic. It's an exercise in constraint. You are trying to force the model to ignore what doesn't matter.
You're putting blinders on it.
Yes. You are telling it, ignore the order of these photos, or ignore the position of this cat. And by doing that, you free up the model's brain power to focus on what does matter.
So don't just grab the newest shiny tool because it's trendy.
No. Look at your data. Ask, what are the invariances here? If I flip this data, should the answer change? If I shuffle it, does it matter? If the answer is no, you better build that into your architecture. You will save money, you will save compute, and you will get a better result.
I want to leave us with one final thought. We started with the bitter lesson, the idea that eventually massive compute beats all this clever design. If everything is really just a graph, and if computers keep getting faster, Are we approaching a time where all these specific designs, the CNNs, the RNNs, just disappear?
Yeah.
Will we eventually just have one massive generic graph model that figures out the structure on its own?
That is the provocative question. If the model is big enough, maybe it learns that images have grids and text has sequence without us having to tell it. Maybe the ultimate architecture is no architecture at all, just a blank slate and a trillion watts of power.
A blank slate and a trillion watts. That is equal parts terrifying and exciting.
Indeed.
Thank you so much for breaking this down. It feels good to finally see the skeleton underneath the skin of AI.
My pleasure. It's always good to see the structure.
And thank you for listening to this deep dive. Go look at your data, find your invariances, and we'll catch you on the next one.